Welcome everybody to the 9th IGAFIT Algorithmic Colloquium. It's my great pleasure to announce today's speaker, Vincent Cohen-Addad, who will talk about graph clustering algorithms, theoretical insights for practice. If during the talk or during the discussions you have any questions, I would like to ask you to use the questions button on the right. And then we can put you on stage and you can ask the question so that everybody can hear. Okay, so yeah, please go ahead.
Yeah, thanks a lot, Christian, and hi everyone. Please feel free to ask any question. If something isn't clear, just let me know. And the goal of this talk is maybe to give you some intuition of which kind of problems so people at Google are looking at, but also are interesting in terms of clustering for graphs. Also from a practical view, from what kind of what theory can bring to the picture, and then ask question if there's. Okay, so this is based on two joint works with a bunch of very nice co-authors with which we did great work. So yeah, so it's based on one paper at Zürich last year and one paper in submission right now. And let me try to go and give some kind of definition of what we are looking for in this talk. So here we are assuming that we are given as input a graph where an edge, and let's think of unweighted graph for now, so very simple graphs. And an edge between two vertices represents some similarity between the two vertices. And no edge means no similarity. So, very basic 0-1 thing. And, you can think of it as a, maybe a social network where you have like friendship, or set of genes where you have some amount of similarity between two genes. Or like the World Wide Web, connection, hyper references between pages. So, very simple problems. And then simple graphs, and of course, the weighted case would be interesting as well, but let's focus on the unweighted case for now. And, finding dense subgraph with little expansion is something that is a very basic problem, for finding maybe communities in social network, or basically group of vertices that have a lot of similarity in common and little similarity to the rest of the world. Of course, if you take a pair of vertices for which there is an edge, this is a very dense subgraph. But of course, if they are connected to the rest of the world, then probably it's not a very good cluster. So what we want is something that has high density inside, and little density to the little expansion to the rest of the world. Okay. And that's what we would like to find in compute in a graph. So the concrete goal for this talk is to give algorithm that identify very dense subgraph with small expansion in sparse graph, or somewhat sparse graph. That's a plus. If we can do it, that's a plus because often these graphs are sparse. So there are not that many edges, but if there are things that looks like cliques. With no thing outgoing, then that's something we'd like to find. That seems interesting. Okay, so as a computer scientist, maybe something we would like to do is be able to quantify this somewhat vague, objective. And I'll propose two ways of quantifying this with two objective functions. So one of them is called the modularity, and it comes from statistical physics. So it's a slightly different. It's a slightly different perspective than what we are used to. And then in the last part of the talk, I'm going to talk about correlation clustering, which is something that it's more classic objective for in optimization in approximation algorithm, for example. Okay. So let's first. One important thing is that something that will be interesting for us also in this talk is, not as a pure theory question, but maybe something that is a good indication as whether an algorithm is practical or it's. Of course, there are algorithms that are practical that don't follow this pattern, but if your algorithm can work in this massively parallel computation model, then it's practical, because it's practical for two reasons. So one reason is that, okay, maybe you can implement it and deal with very large data sets and, big companies are happy. The other reason that I prefer is that then it's probably that is an algorithm that is simple enough, that does some kind of basic enough operation that I would be tempted to implement it. It's like I wouldn't be afraid to implement it. So, I mean, of course, you can have complicated, massively parallel computation algorithms, but in general, if you can find such an algorithm, maybe that's good. Okay, so this model is the following. You have think of the total size of the input is the number of edges in the graph, and we have a number of machine P, which is sublinear in the input size in M. It's like M to the delta for some constant delta in 0, 1, let's say, just simplicity. And I give each machine unlimited computation power, so you can solve like NP complete problem there, whatever you want. It's fine. But the issue is that they have only like M over P memory. They don't have that much memory. It's like they can't store the whole input. And so to solve the problem, you will need the machine to communicate, to exchange information. And in each round, each processor sends or receives like M over P bits of information with any other machine, with the other machines. There is no topology in the communication. We don't care. Like it's a click if you want. You can exchange all information with all machines. And the thing that is we would like to minimize here is the number of communication rounds. Okay, so if you can solve the problem in communicating very few information, that's great. If you can't, then that's a problem in practice because you have to make many rounds. Okay, so now let me turn to the objective function. So I'll keep this model in mind. Like the algorithm I'm designing, they work in the classic setting, but sometimes I'll just appeal to this model to try to see like what can we say in this model. Okay. And the first problem I mentioned is modularity. So this objective function that comes from statistical physics, and which can be a little counterintuitive when you first see it. So let me try to explain it in a reasonable way. So you have a graph G, and think again, an edge between two vertices means there are some similarity between the vertices. And what you want to find is a partition into clusters. As many as you want. So here I put K. It's up to you to choose K. Like it's not constrained. And you want to maximize the following objective. So you will take the sum over all clusters, and then you will gain 1. You will have a score of 1 for each edge that belongs to the cluster. Like if UV is in the cluster, then you gain 1 if there is an edge between them. But you pay for all pairs, you will pay the product of their degrees divided by twice the number of edges. Okay, so why not? But why do we do that? Okay, so the intuition from the people who designed it, like 10 years ago on statistical physics, was that it's for a given cluster, it's a function that compares the number of edges that you have in the cluster, which is this first term, to the expected the expected edge you would have in between these two vertices in a random network where the degree distribution is prescribed, right? So if I try to do a random graph where I say that the degree of u is du here, the degree of v is dv, then probability I get an edge between these two vertices in this graph is this. And so it's a kind of a null hypothesis that you are trying to compare to. You are trying to see how many edges you have in your cluster versus like what you would have in expectation. So this is a nice okay. So I mean, maybe it doesn't look that nice first, but why is it nice objective? It's nice because okay. So first you have like it's kind of normalized in the sense that if you put all the vertices in the same cluster, then your modularity is 0, and this is independent of the graph you are working with. This is independent from your input graph. And then, then from there, you can try to get higher and higher modularity by putting some of the vertices together. Okay. And something that I like here, and I think that's why it's a nice objective as well, is that, if you give me, okay, of course, if you give me 2 division click, with no edges in between, then the max modularity clustering is to put these 2 clicks together. Now, if I come and I give you another graph, and now I give you 3 division clicks, then again, the max modularity objective is to put these 3 clicks in different clusters. And it's kind of, the nice thing here is that the number of clusters is not hard-coded. So it depends on the function. So if you give me a graph where the right number of clusters is k, then it's going to try to output k clusters. If you give me a graph where it's like K prime, then it's going to output K prime clusters. It's not hard-coded like some other objective, like metric objectives, where you have like K means, K median, and so on, where K is like part of the constraints. So it's a very so from that matter, it's a nice objective. And if that's the first step, is to phrase it as an objective optimization problem. So maybe that's the optimization problem we want to work with, at least for some part of the talk. And then now we need to find an algorithm for finding for optimizing this quantity, for finding a clustering that maximizes the modularity. Okay, so there is this algorithm that is a very natural approach. It's called the Louvain algorithm, because the people who designed it in Louvain, in Belgium. And so it's a natural approach for maximizing modularity. It's very simple. So this is not quite the Louvain algorithm. It's something that is a little variation from it, because it's a slightly more simplified, simplified variant that I just present here for the sake of simplicity of the talk, and just to give you high-level intuition. But it's very like the most naive algorithm you can think of, is that you start with a partition where each vertex is in its own cluster, and then you try to iteratively improve the partition by moving vertices from the current part to another part if it increases the modularity. It's like, if I can move U to the part VI, then if that increases my modularity, I just do it and then I repeat. So maybe you need to randomize it a little bit, like maybe among all the one that I think that what people do in practice as well, is that if you want to, if you have many possible vertices that would move to some part and that increase modularity, then you pick one at random, you do it, and then you repeat. And then when you can't increase anymore, and you're in the local optimum in terms of modularity, then you output this clustering. That's your solution. The real Louvain algorithm does some little extra steps to repeat this process and try to avoid some local optima, but let's not go too much into that. So now you can ask, okay, it's the most naive algorithm I can think of, and now how good is this algorithm? Probably because it's the most naive one, maybe it's not super good. And okay, and here there are two answers. So the first answer is like the one we expect, which is that it's awful in theory, that you can't prove anything about this algorithm in the worst case. Even like, for kind of small families of graph, like, if I try to, restrict my attention to, I don't know, planar graph, or like, what kind of, any kind of little small family of graph, you can come up with very simple, counterexample where the algorithm is stuck in a local optimum that is really bad in terms of modularity. But then in practice, it's surprisingly good. It's now one of the methods of choice for clustering graphs. The paper has like I think now it has like more than 10,000 citations. It's really like something that is like the baseline. I mean, if you come up with a new clustering algorithm for graph, probably you should also compare. Like, if you want to convince people to use it in practice, you will have to compare to this thing. So it's a very we are here like having a big gap between like what's happening in theory, what's happening in practice. There is like a misconnection. Okay. So what we tried to do in this paper was to try to understand what are the mechanisms behind Louvain, the algorithmic idea behind Louvain that makes it work in practice, and try to prove something or understand when it works, when it doesn't work. Because maybe the worst case instances, they're like a bit artificial, a bit like not really modeling what's happening in practice. So it's not. So what we started with is the stochastic block model, which is a very classic random graph model for generating graphs that have like underlying ground truth clusters. So I'm going to take the most basic stochastic block model you can think of, which is that we have two. So there are n vertices, and then there are two parts, A1, A2. Each they are both of same size. It's a partition of the graph. And then we have an edge between U and V that is generated independently with probability P if U and V belong to the same part, AI, or with probability Q if they are in A1, A2, like in different parts. And P is larger than Q. And your goal now is to find these two underlying parts, A1, A2, to find them, find an algorithm. Of course, you can't find it for all possible values of Q, P and Q, but there are like, some non-trivial bounds, like if P and Q are like constants, then it's kind of easy, somewhat easy. And then there are some kind of gap that is like the information limit threshold, information theoretic threshold, for which if the gap between P and Q is smaller than that, then you can't do much because it's like a total mess. But there are some regime for which like we can. And now, the natural question you can ask is, this Louvain algorithm that performs so well in practice, maybe it does perform well in practice because there are kind of clear clusters in the graph that we want to cluster in practice, and then that's why it performs well. And maybe that's why we need to do, because in the worst case, maybe there are no clear cluster, and then it does nonsense. And then now you can ask, how does it perform on this stochastic block model, given that there are so clear clusters? It should work. So that's what we try to prove. So that's the theorem we proved. We showed that if the difference between P minus Q divided by square root P, this is like the variance, is larger than 1 over n to the 1/6, then Louvain will indeed find A1, A2 with high probability and in near linear time, which is what people see in practice, is that they see a near linear time convergence rate for Louvain, even though the worst case could be like n squared or something. So it seems to be even faster than what can happen. So that's the theorem we proved, and okay, we can improve, like this n to the 1/6 is you should, if you want the information theoretic limits here, you would have to replace 6 with 2. It's like kind of still somewhat far from the information theoretic limits, and we are not showing that Louvain is as good as like a spectral method for finding these things, which are like kind of the best known. It's like a combinatorial algorithm, it's somewhat simple, but it does something reasonable. It's non-trivial. It is bound to achieve, at least. Okay, so that's one thing, and I want to give you a little bit of the techniques, maybe, and then I'll explain a bit more what are the possible interesting outcome of this line of thought. Okay, so the technique and proof idea. So the proof is kind of split into 2 parts. So the part 1 is to say that at the beginning of the algorithm, you don't have a strong signal. You don't really know which one should go with who, and so on. It's like very messy what's happening. But we can show that on average, Louvain tends to do the right thing. So it will place vertices from A1 into the part that contains the most vertices of A1. So it kind of starts aggregating vertices of the same community into the same cluster. But this is on average. So it's not that easy. And then we have a second part, which is part 2, which is much better. I mean, it's actually also much cleaner, because in that part 2, we can go down, like we don't require bound on P and Q that are as loose as what we have in the rest of the proof. The bound on P and Q are close to the information theoretic limits that we require for the second part. So it's pretty okay. So the second part says that if you reach a clustering where you have one part, you have 2 parts, and then one of them contains significantly more vertices of A1 than of A2, then you will make more with high probability. Then you will make good swaps, and so you will convert very fast, very quickly. So at some point you reach, there's kind of a threshold phenomenon that at some point, when you have one part that is made of 51% of elements of A1, then it's clear what's happening, and then Louvain makes only good swaps. And it's kind of funny, because there's it's not like a continuum proof that you can apply and then it gets better and better. It's like 2 different kind of argument that we have there. Okay, so we made some simplification and assumption here. Some of them are needed for the proof. We don't really know how to deal with them otherwise. Some of them are just for simplicity in the talk. So assumption 1 say that, okay, let's start with a random 2 partition, V1, V2 of equal size, okay? And we assume without loss of generality that, V1 has slightly more vertices of A1 than of A2. But of course, we don't know which one is V1, which one is the one that has more. But we just say that, okay, one of them has slightly more of A1. And, what we say is that it's of course not 51%, because if it's 51%, then it's part 2, we're happy. But if it's like, it's like 50% plus square root n, which is like, tiny. It's like what we get if you take a random 2 partition, like which you would get with constant probability. And then yes, so that's the first assumption. I don't really know how to remove it. I mean, I'm not sure it's that easy to start with, the real Louvain, which says that okay, you start with everyone on his own cluster. But yeah, that's it. And assumption 2, we move one vertex to the other from Vi to Vj if it has more neighbors in Vj than in Vi. So it's not quite the modularity. It's just the number of neighbors. We can handle the modularity, but this is just for simplicity for the talk. So this is just looking at the number of neighbors instead of the value of the modularity, but this is only for the talk. So right, so if you have a vertex here that has like 7 neighbors in V2 and 6 in V1, then you will move it. I mean, you will pick among some of them that want to change, you'll pick one, and then you move it. Okay, so this is the algorithm. And what we do is that we need to measure how much progress the algorithm do. So we have that delta is the number, is how much above 50% you are in A1. So in A1 in V1 we have most vertices are from A1, and we start with 50% plus square-root, and now we want to count how much higher than 50% we are. So it's like 50% is like n over 4. So we just count how much we have. And at first, as I said, it's like square-root. And now we want to increase delta. We want to make sure that, okay, delta is going to increase as much as possible, and when delta is like n over 4, then, we have classified everyone correctly, so we're happy. So the goal for us is to increase delta. Okay, so for each vertex u in A1, we have that in expectation. This is just like writing down the expectation. Because there are slightly more vertices of A1 in V1, we have that the degree of u to V1 is larger than the degree of u to V2 plus delta p minus q. So in expectation, we are happy. In expectation, u is willing to move to the right side. Okay, if u is in V2, then he will go to V1. If u is already in V1, he doesn't want to move away. So we are happy. In expectation, the expectation of the degree is good. Of the changes is good. So from there, you can have the following lemma, which says that the probability for all v in A1, the probability that the degree of v to V1 is larger than the degree of v to V2 is at least 1/2 plus some kind of the signal, right? So p minus q divided by square p. So that means that with probability 1/2 plus a little epsilon, we are doing the right thing for a given vertex. I mean, either we are letting stay in V1 if it's already in V1, or we are moving it to V1 if it is in V2. Okay. Okay. So basically, if I just wanted to say that, the first move that the Louvain algorithm is going to do is good, well, then I'll be happy because I'll say, okay, with constant probability, with 1/2 plus epsilon, I'm going to do the right thing. I'm going to increase delta by 1. Okay, so that's okay. That's interesting. I start with a random partition. I do one move of Louvain. I increase the delta by 1. Okay, great. But the thing is that we would like this to be true for many steps, right? Because maybe with 1/2 plus epsilon, I increase delta by 1. With 1/2 minus epsilon, I decrease it by 1. So I will need to repeat this quite a bit if I want to, increase my delta to something large, for example, or to even classify everyone correctly. I need to do many, many swaps because every time it's only with probability 1/2 plus epsilon that it's increasing. So what we do is that we can try to have to show that this here is going to be true with high probability. So here it's a little bit of a mess of there are different probability, right? Because there's a probability that comes from the random partition I'm taking at the beginning, and there is the random probability of the edges. And these are two different sources of probabilities, right? Because of randomness. So in terms of the randomness coming from the edges, then I know that each edge belongs to at most 2 neighborhoods. So in fact, they have not that much impact. They are what we call 2 read. And so we can still have some kind of concentration. We can say that, okay, now, given the randomness I have on the initial cut, the probability that this happens is going to be highly concentrated with respect to, it's going to hold with high probability over the edges on the input graph. And we can say that these hold with very, very high probability because we can almost use a Chernoff bound here to say that this is gonna be true most of the time, because these variables, the neighborhood, the degrees are almost independent. They are almost independent because if you take two neighbors, if you take two vertices, if I compute the degree of one or the other, they are not. Depends only on the edge that is in between. So the independence the dependencies between them is really tiny. Okay. So what we can say is here, which is like, I'm not giving too much detail because I want to go too much into the technical details. I'm saying like, if you have with good probability, this can hold for many steps over many different cuts that you can have. So this high probability statement, there is a way to translate it into, I can repeat this argument during n to the 2/3 steps. Okay, so here this n to the 2/3 that I have in the exponent, I can say, okay, this statement is going to be true for n to the 2/3 steps. For n to the 2/3 step, I have this 1/2 epsilon probability of making the right thing. And so if I assume that p minus q over square root p is greater than 1 over n to the, or there is minus here, 1 over n to the 1/6, then after that many steps, after n to the 2/3 plus epsilon steps, then my delta has increased by enough. I increased by a lot, in fact. And enough to make something significant. Like almost reached. I'm reaching this 51% that I was saying before. Okay. There is a more careful analysis, which I think is nice. I don't want to go too much into the details, but there is one thing that I didn't say here, is that here, like, this crude analysis is really looking at which edge is going where, and or whether this edge exists or it doesn't exist, probably P, Q, and so on. In fact, when you make this type of argument, that's not really exactly what you want to know. Like, if I look at one vertex, you don't really care whether it's connected to, to who it's connected on the other side. You just want to know how many neighbors it has on the other side. So there is a much weaker. You don't need to do that to use so much randomness from the generation of the graph to be able to make this type of argument. So there is a slightly better proof there, but let me avoid. Because I want to talk quickly about the step 2, which is what happens when now delta is like 1%. Like you have reached a place where you have 51% correctly classified vertices into V1. And then here we have a different argument which says that if you look at the subset of vertices of V2 in V2, but that belong to A1. So these vertices of V2, they should go back to A1, but for now I'm looking at the subset of S such vertices of size n to the 1 minus epsilon. We can show that the sum of their degree is to V1 must be larger than the sum of the degree to V2. So namely, what we are saying is that there is no subset of vertices of A1 misclassified of size, n to the 1 minus epsilon that will want to stay in the misclassified region. There is at least one vertex in that group that wants to go to the other side. I don't know how many of them, but I'm just saying that, if you take big subset n to the 1 minus epsilon of misclassified vertices, there is at least one of them that wants to go to the other side. And that's because delta now is really large. You have strong signal, so you can't have large group of vertices for which it's bad. And then from there we can show that it's such a overwhelming probability that we can show that now the algorithm is gonna increase delta with a probability 1 minus 1 over log n, so much higher than what it was before. It's not 1/2 plus epsilon, now it's like 1 minus 1 over log n. And then, if you have these, like you increase delta with that rate now. And if you increase delta with that rate, then you converge to the right partition in nearly linear. So that's the second part of the proof, but it's kind of different. Like the other one is talking about one vertex at a time. This one is talking about subgroups. It's saying like there is no bad subgroup. The first part is saying, okay, each vertex is more or less good. The other one is saying, oh, there is no bad subgroup. So it's a little bit, maybe it's possible to improve that view. Okay, but what let's not go too much into the details. What are the outcome of this? So one thing is that you can adapt this proof to make this apply to the parallel version of the Louvain algorithm that I described. So now let's say that the algorithm is not that you pick one guy at a time to change stuff. You just have your two partitions. Everyone who wants to go to the other side because he has more neighbors there, you just move them all directly. Everyone who has the other side wants to go to the other to the first part because he has more neighbors, you just do it as well. Okay, so like very parallel, very, very parallel. Like it's almost like, it's a distributed algorithm. Like, everyone is responsible for one node. If this one node wants to go to the other side, just do it, move it right away without waiting for anyone to do anything. Just do it. And then we can show that in that regime, with slightly better dependency on P minus Q, with slightly better bounds, closer to the information theoretic threshold, we can show that in a constant number of these communication rounds, the algorithm will converge to the ground truth partition, the A1, A2 partition. And we're thinking about that, and I was having fun, so I wanted to mention that. So let's say now, because this is so parallel, let me think now of the following thing. We are in the social networks, and you are connected to people who believe like you with probability P, and people who don't believe like you with probability Q. P is larger than Q. And now a random event happened. So everyone has some opinion 0, 1, stuff like that. And now you start following the opinion of your of the majority of your friends. Okay, so if the majority of your friends is convinced that your opinion should be 1, then you start to be 1. If it's 0, you start to be 0. And then what this proof shows is that if there is some kind of separation between these two communities, then you will quickly converge to very polarized opinion. Like one group will be 0, like in a constant number of parallel rounds. So in a constant of time where you change your mind, you will be moving to one group being totally 0, the other group being totally 1. And I think it's I think this is kind of amusing, and we can try to maybe use this type of proof and algorithmic idea to I mean, like, there's a lot of work in like belief spreadings and but it's this is like in the stochastic block model, so maybe it's meaningful for representing some of the social networks. Okay, so let me just then I'll talk briefly about correlation clustering, but let me give you some open problems. So one shortcoming of the what I described before is that we assume that the two communities are roughly the same size. The initialization is also done with like two equal size parts. So can we rely to these things? Like it's what we did is interesting because it starts making progress towards understanding why Louvain works, what are the arguments that we can try to have, but what are the algorithmic insights we can try to use for improving it. But it would be good if we can show that it's robust to inputs. Maybe actually it's not that robust. So maybe if you try to find better heuristic, you can try to actually improve Louvain in that way. Of course, if we can also move to a better model for real-world graph, like beyond the stochastic block model, maybe like semi-random graph model, where some adversary can come and corrupt some of the edges. Can we have an MPC massively parallel algorithm for this? Again, same thing, MPC algorithm for exactly covering the stochastic block model up to the information theoretic threshold. Like there is a clear bound that you can achieve with like semi-definite programs, or like if you are okay with a constant, spectral algorithm suffices. But can you give an MPC algorithm with very few rounds of communication that will give you that will reach the information theoretic threshold? Okay, and can we understand a bit better this local dynamics in networks? Different objectives possibly. Okay, and I'll if there is any question, I'll go there, because you can ask them now, because otherwise then next will be the correlation clustering. It's a little bit different, but it's not that different. I mean, at the end there will be time for question anyways. But if you have any question right now, you may want to ask. Okay. Otherwise, I'll just continue on correlation clustering. And for correlation clustering, now it's it's closer to, you know, what people doing maybe like, you know, combinatorial optimization are used to. We have this very nice objective function, and we try to get the best constant factor approximation for it, something like that. So the input is very simple. It's like you have a complete graph. Each edge E is labeled, you know, either plus or minus. And you want to find a partition into as many clusters as you want, such that partition of the vertices, such that, you know, if you have plus edges, you will pay for each plus edge that goes between the two different clusters, and you will pay for each minus edge that lies within one cluster, that are internal to a cluster. Okay, so you want to really, you know, get clicks, right? And like, you know, clicks are like 0 and so pay, you know, you pay for these things. In practice, we can think of this objective as meaningful in the setting where, you know, your minus edges are the no edges of the graph. Like, you know, you get the graph and unweighted graph, and like, you know, no edge are like minus edge, and plus edge are like normal edges. For finding communities, for example, I think that model makes sense. And there have been a lot of work on this area, but maybe let me give you the two most famous algorithm maybe. So there's a simple pivot-based tree approximation by Elon, Chaika, and Newman, which is very simple. It's like you pick a random vertex, pick this guy, then look at all the plus neighbors, and then grab them, put this guy with them. That's one cluster. Put it aside, you output it, and then you recurse on the rest of the graph. So very, very simple algorithm. And there is an LP-based rounding approach, which gives 2.06, which is better, which is by Shola, Makarychev, Tram, and Yaroslav, which consists of like solving the LP and then doing the more or less the same pivot algorithm, but you will throw coins to decide whether you attract people with plus edges or minus edges, whether they come with you in the cluster, based on the LP value and whether they are plus or minus edges. So these are like two very classic. I mean, like the 2.06 is like state of the art, and, you know, the 3 is like one of the most popular algorithms, like most famous algorithm. And this objective is really nice, right? Because again, you have the same features on the modularity one, I think, which is that if you have disjoint clicks C1 up to CK, then the correlation clustering cost will be 0, and you will have, and the objective is to put them in different clusters. So again, the number of clusters is a function of the input. If you come with 10 clicks, then, you know, I need to output 10 clusters. 100 clicks, I need to output 100 clusters. So it's pretty nice. It's like really unsupervised, right? You don't have to know anything about your input for being able to, you know, do something. Okay, so what do we really want? Let's think about this objective function and what we are really after. So, you know, we really want very dense plus edges subgraph that have very little plus edge expansion, right? Why? Because, you know, what I can say is that there is a constant factor approximation. I can try to convince you of this in like 1 minute, is that there is another one approximation such that all my clusters have plus edge density very close to 1. Like, let's say that larger than 0.99. Like, you know, almost all edges inside the cluster are there, like, you know, 99%. Because, you know, if that's not the case, then what it means that I have a lot of minus edges inside. I have a significant fraction of minus edges inside. So I'm already paying a lot. So, you know, if I'm only after a constant fraction approximation, if I have 10% of my internal pairs that are connected with minus edges, I might as well pay a factor 10 and make everyone singleton vertex. And, you know, okay, what's the cost increase? The cost increase is the number of plus edges, but that at most 10 times higher than what I was paying before. So if I have a cluster that is not super dense, then, you know, I might as well just discard it and get rid of it in my constant factor approximation. I can just say, okay, then make everyone singleton. And then there is this second bullet, which is also, I think, nice, which is that each vertex has 0.9 fraction of its plus neighbor inside its own cluster. Because if you give me a solution where I have, you know, 20% of my plus neighbor outside, then what I can do is that I can make this guy a singleton. I'm already paying 20% of my plus neighbor. So maybe now I'm paying the 80% more. Like, you know, 80% remaining, I'm also paying them because they're in the same cluster. If I put that guy a singleton, I'm going to pay for these edges. But, you know, if it's only a factor 8. So, you know, if I care only about constant factor approximation, you know, I can just put this guy aside. So these two things are really saying that what I'm after here are like super dense subgraph with very tiny expansion. Okay. So then we have this key insight, which I think is a cute one, is that if you pick two vertices of the same cluster in your constant factor approximation, or in the optimum solution, if you want, then if you look at the neighborhood, you can look at the rows in the adjacency matrix, like the vectors, if you want, or you can look at the neighborhood sets. Then the symmetric difference should be not too different, right? Just because of what we just said before, the symmetric difference between neighborhood of vertices in the same cluster should be almost the same, except maybe for a little constant factor. So what we have is that we can show this lemma, which is that there exists an order 1 approximation. Of course, there is a parameter you can play with, such that for any UV in the same cluster, then what I like, because I do metric clustering as well, I like to see it as the vectors of the two entries in the adjacency matrix, very close distance. They are very, very close, like in terms of their total norm. So they are very similar. The number of, it's only a constant factor. They can differ only by a constant factor. And so what we say is that vertices UV that have the symmetric difference in their neighborhood smaller than the epsilon times the max of the size of the neighborhood, the max of the size of the neighborhood, are in agreement. We're going to call them in agreement, and what we really care about are vertices that are in agreement. And so now, and it's good because I don't have that much more time, but I want to describe a very simple, like the most basic algorithm you can think of for finding a constant factor approximation for correlation clustering, and it's an MPC algorithm because it's really, really simple. So take your graph. It's like, yeah, I mean, I'm hoping that everyone can get that, so because it's really cool that it's so simple. So take your input graph and discard all the plus edges between vertices that are not in agreement. As I said before, if two vertices are not in agreement, we can just, they should not be in the same cluster, so, we don't care. So we know they are not in the same cluster anyway, so by turning these plus edges into minus edges, we don't lose much. Okay, now look at the resulting graph and say that the vertex is light if the plus degree of that vertex has decreased by constant factor. So you have a vertex if he is not in agreement with many of his neighbors, then this guy is going to be light. It's not really okay, because the intuition here is that dense little expansion subgraph, they are made of vertices that are in agreement because they are very, very dense and very little expansion. So their neighborhoods are really, really similar. So they are all in agreement. So if you have very dense subgraph, they are made of vertices in agreement. So these guys will not be, the guys in the same cluster, they will not be light if you are in the dense cluster. So, okay, so all the vertices that are large, that have lost most of their plus degree at the previous round, we call them light, and we discard plus edges between light vertices. And now we are done with we are left with a graph where we remove plus edges at the two previous steps. And now it's a very, very simple algorithm. You just compute the connected components of the resulting graph. Okay, so you have your graph, you remove the plus edges between vertices not in agreement, plus edges between light vertices. Now compute the connected component of the resulting graph. These are the correlation clustering cluster. So it's just like connected component. Okay, and on top of this, we show that the connected components that we get at step 3 have diameter at most 4. So in fact, this can be done very efficiently because connected component in massively parallel or distributed environment is something that is not that easy. You often pay the diameter, or at least log the diameter. So here we are thinking that, okay, it's at most 4. So it's okay. We can compute the connected component of the resulting graph. And these are the cluster you want to output. And the idea is that, again, the densely connected subgraph, they are made of vertices that agree between them. And so that will remain not light. They will be heavy vertices. And then they are tightly connected. So their diameter is very, very small. And maybe you will attract some of the light vertices, but you can't, they are a distance 1 hop away or maybe something like this. So it's not too bad. And you can't have clusters that connect to each other, because for 2 clusters to connect and have end up in the same connected component, you would have heavy vertices of the clusters to agree, to be in agreement, and this is impossible because heavy vertices are little expansion. Okay, so that's okay. So that's a very simple 3 steps MPC algorithm for correlation clustering, constant factor approximation. So very, very simple, constant number of rounds of communication. So really the simplest we can think of. And so we have a theorem. Yeah, that's what we showed, that constant factor and constant many rounds. Okay, so here I'm happy to brag about the number of MPC rounds because I think it's like maybe less than 15, maybe close to 10. This thing here, the constant factor approximation, this is embarrassing. I think the constant right now is like 100 or something. So it's not that great. I mean, like the constant factor approximation is not super nice. And okay, the total, I should say that the total memory here is the number of plus edges. Right? It's order number of plus edges. So it's like you don't have to store the n squared size input graph for correlation clustering where you have plus and minus. You just have to implicitly just get the plus edges. Okay. But okay, so when we saw this constant that was pretty large and so on, then we tried it on some data sets. So DBLP is the small one, but the other one are start to be quite big. And we tried this MPC algorithm, and we looked at the correlation clustering objective value that we get with our solution, with the solution that other people compute. So we have our algorithm with different parameters for the definition of agreement, so different definitions, different parameter value. And also there is a pivoting algorithm. And our algorithm is really efficient, in terms of correlation clustering cost. It's much better than the pivot, even though the approximation guarantee that we can prove is bad, it's still better than the pivot. And I think the reason for this is that, even though the pivot is 3 approximation, I think the reason for this is that the pivot can do very weird thing in the sense that it can take, if you pick an outlier and then you start, if you have few outliers here and there, and at some point you pick one of them as a pivot, then you can start aggregating vertices. You will take your whole plus neighborhood, and there is no chance, maybe little chance in this real world graph that the whole plus neighborhood is going to be a dense subgraph. So, of course, in terms of correlation clustering cost, it's not too bad because this has low probability, but this still happens, I think, in a few cases. And in these cases, you are paying really a lot of cost because you are aggregating a sparse cluster. You are defining a sparse cluster. Whereas our algorithm is, by definition, is not going to take any sparse cluster. So it's kind of robust to outliers. I think that's the main thing, is that, yeah, maybe that's the better way to put it, is that I think this algorithm is slightly better because it can remove outliers that happen in practice that can fool, the pivot algorithm in terms of approximation guarantee. Okay. And let me finish maybe with some open problems, and then I'll take some questions. So, right. So as I said, the approximation guarantee we prove is so bad that I didn't dare put it here. But I think it's a good open question. If you get a better approximation guarantee, again in still R1 MPC rounds, that would be nice. And okay, I think I would like to look at the next step, which is that now for the weighted version, where you have weights on the edges, weight on the plus edges, one on the minus edges, and now the objective is also weighted. Then there is another log n approximation, offline, a standard offline algorithm, not sequential algorithm that, can we get another log n in, constant number of MPC rounds? I know other log n is going to be solving multicut. If you improve this, it's not going to happen right now, but if you can reach the multicut bound in constant MPC rounds or in log n MPC round, I think that's already interesting, because sometimes we have to deal, often we have to deal with weights as well. And again, there's also an FPT approximation scheme, running time f of number of cluster you're looking for, f of k 1 over epsilon, that gets you a 1 plus epsilon in offline. And I'm saying, can you implement that in a few MPC rounds? Parameterized by the number of clusters. I think that's a pretty cool open problem as well. And I'm gonna stop here, and thank you for your attention, and happy to take questions.
Yeah, thank you very much for this very nice talk. Are there questions in the audience? So if you have questions, you can use the question button on the right. Maybe let me start with one question. Oh, there's first question. So let's see. I was supposed to be able to move the person to the stage, but I just don't see how to do it. So maybe let me just say what is the question. So the question is, what were the different parameters next to the pivot algorithm?
Right. So good. So good question. So the thing, the pivot algorithm has no parameter. So yeah, what we did here is that there is so let me actually maybe show the curve again. So the real pivot is this yellow one here. Is the real pivot, but it's a bit too slow for this large graph. So you can see it here on the BLP. That's the right pivot. And then we have these other pivots that are implementation of this. It's an implementation of the pivot in the MPC setting where they do some approximation on the, because the pivot algorithm is really sequential. You have to pick pivot one at a time, and so they have some kind of ways of parallelizing it. So it's referring to a paper. I should point to the paper actually that has some parameter for the way they will relax the sequentiality of the pivot algorithm. So then this introduces some other mistakes, but then you can tune the parameter of how much sequential you want it to be. And so the higher the parameter, the more sequential it is, and so it controls the parallelizability of the pivot. Yeah, because the pivot by itself is really too slow for these things.
So if I view the correlation cluster, or if I run some Euclidean approach on the correlation clustering input, and maybe I do this on the low rank approximation, do I get same results? So it seems to be kind of similar.
Yeah, exactly. So yeah, this I would like to do. So yeah, exactly, because I think I really like this view of seeing this agreement as vector closeness in terms of vector in this in terms of this. So there is one little thing is that the distance is small when you normalize by the size. So I think a low rank approximation or something like that may work. So yeah, so maybe a very bold conjecture that I would make would be, can you prove that a low rank approximation on the correlation clustering input helped you get a constant factor approximation for correlation clustering? That's that would be great. Yeah, that would be very nice. Yeah.
Okay, thanks. So there's another question. In the Louvain part, in the Louvain algorithm part, what is the obstacle of generalizing your analysis for 2 clusters to K clusters?
Good thing. So that's a tough one. So man, that's so this right. So the main issue is that one of the main issue that you are saying is that the signal. I mean, the signal is really poor in the sense that we are really seeing this signal here. It's really poor. So now if you have K parts that are maybe I should say the bottom line is that you can extend the analysis that I did for 2 parts. You can generalize it to K parts, equal size K parts. But then the probabilities, the dependency on P minus Q starts to increase. There's a dependency that increases in K that is worse and worse in K. And so the bottom line is you can do it. but you don't get good bounds. And the reason you don't get good bounds is that now the signal that appears on this slide seems to be kind of drawn into the K part. And if you have some parts that start to be slightly more dominating, you this. And okay, one thing that is very hard in this is that if you have a part that is slightly smaller than the others, then you have a rich get richer phenomenon. Because now if I look at if I'm another vertex and I compare one tiny part with one big part, even though the tiny part in proportion can contain more vertices of my own community than on the other community, then if you just count the number of vertices, then you are tempted to go to the bigger one just because it's bigger, not necessarily because it has, P and Q thing. So I think then in that case, you may need to kind of normalize, like, you have to somewhat change the Louvain algorithm to normalize by the degree divided by the part of the size or something like this. And that's and I think that's a very nice direction if we can prove something like this that would work.
So what is known in the non-parallel setting for correlation clustering?
Yeah, so this is the minimization version where you want to minimize the disagreement, the thing that does it. And so okay, so I think pretty much what I wrote here, I mean, I hope I'm not forgetting anything, but for the minimization version, so there is this 3 approximation and 2.5. You can make it 2.5 is to do LP rounding, pivot-based LP rounding with a naive LP rounding, and 3 and 2.5, and then 2.06 is like a clever LP rounding approach for this. And in terms of offline setup, I think that's the best. Then there is the FPT setting where you have parameterized by K, and in which case you can get 1 plus epsilon, but it depends on, if I'm not mistaken, I think you can get 1 plus epsilon in 2 to the K poly n. And that's what's known. And and I should say low bound is like really, I mean, it's APXR. You can't get the p-task for this one, but it's like 1.11 or something, like 1.01 or something. It's like it's not that good. The hardness of approximation.
Are there any more questions? So this does not seem the case. Then let's thank Vincent again for this very nice talk. And let me invite everybody to join our network session, which happens after this talk. Thank you very much.
Thank you.